as you can see, I am presenting Choreographies Meet Communication Failures, which is joint work with Fabrizio, Montesi, and Marco Peressotti, who are sitting here as well. So if there are any problems with it, it's our fault. You've probably seen something like this if you've looked at anything about choreographies. So the communication works in choreographies is you write something like this, which says P sends 3 to Q, and Q stores it in X. And then you project this to two different primitives at P and Q. So at P it says send 3 to Q, and at Q it says receive from P and store in X. And then, at the local level, we assume that these two synchronize, and Q then just has 3 stored in X. As it turns out, sometimes that doesn't happen in the real world. Sometimes communications fail. And then we ask ourselves, well, what do choreographies look like if, they have realistic communication? What does that mean in our case? Well, it means A, it's synchronous, and B, it can fail. And we consider 3 different kinds of failure. Number 1, send omission. P tries to send, doesn't go well, the message never reaches the network. P knows that this has failed. Second failure, receive omission. Q tries to receive, doesn't have anything to receive. The message hasn't reached Q yet. Q knows that this has failed. And the third is omission failure. P thinks it's sent something successfully, but somewhere on the way to Q, the message gets lost. And neither P or Q knows that this has happened. So now we ask ourselves, if we don't have this, nice little one singular communication primitive, what's even the point of using choreographies? What guarantees can we get? Are there any of these guarantees that are easier to get for choreographies than for just writing code separately for our participants? So what I'm going to tell you about our contributions here. 1, we have a choreography language which has failures in the semantics. 2, we have some choreographies written in this language which describe ways of recovering from failure. And 3, we have a way of statically analyzing these choreographies, which, hopefully we can get some guarantees that are interesting, and we can take advantage of the fact that we have written our program as a choreography. So first of all, what does our language look like? Looks something like this. So we traditionally, you have our communication here. So in our language, instead, we have 3 steps to a communication. First is we declare a communication. This communication is going to be called K at P and K prime at Q, and it communicates an int. We have a type system. I'm not going to talk about it. It's not very interesting, but it's there. It does what you'd expect it to, more or less. So once we've declared a communication, we implement it. First by writing that P sends 3 on K, and then Q receives something on K prime and tries to store it in X. So I'm going to go through the semantics of this in a minute. First, going to just talk about what K and K prime are, because these are the interesting parts of our syntax. So K and K prime identify the communication at P and Q respectively. So what we do is that P and Q count their communication. So this is K is the first, P knows that K is the first communication with Q. Q knows that K prime is its first communication with P. So when P sends something on K, it tags this with a 1, because K is the first communication, and correspondingly Q, then when it's trying to receive prime, it only looks at messages that are tagged with 1 and are from P. So that is how our communications, we avoid any mix-ups where P and Q disagree on which communication is which. And look at that, we already have a benefit to using choreographies, because since we only count when we have this primitive declaring a communication, and since this is one local action each at P and Q, and this is the only way P and Q can increase their counters for their communications. We can ensure that the counters stay in lockstep. Mm-hmm.
Move the away from the strap.
Oh, sorry. Whatever. Sorry, yep. Anyway, so let's look at our semantics. Our semantics looks like this. We have triples consisting of a choreography C, a local memories of the various processes, sigma, and a set of messages in transit K. And the messages in transit looks like this. So P is sending to Q the mth communication between P and Q, and it's sending 3. And this message is, if it's in K, it's in the network, and it can get lost, or it can reach Q. So what does our, one, there we go. So this is our desired outcome of our little communication. So what we're hoping is that starting from up here, we have our, our little choreography that declares a communication and executes it. And what we want to happen is that first we declare, which updates sigma prime, so the counters for which were 1 before are now both 2, and also we have the state of frame 1 from at P communicated with Q is bottom, which is to say we have not sent anything, and conversely at Q we have a receive frame which also has not received anything and therefore has the state bottom. From here, what we would like to happen is that we send something which updates the send state to yes, we have executed a send, and adds the message to K. And then we can move the message, communicate it, so that it gets to the receive state of Q. It is ready to be received, and Q can execute the receive and say now X is 3, and we have successfully received 3. According to the state of our receive. Obviously, since we have failures, this is not always what happens. So one thing that might happen is that we fail to send, and instead we don't add the message here, but we do still take the send, and we also don't update our state so that the sender knows that it has not yet succeeded in sending. And there's no message. Another thing that can happen is we might try to receive and too early. So if since Q is not, Q and P can execute concurrently, so Q might try to receive already before the send has even happened. And in that case, again, nothing really happens. We just consume the send action, and we're stuck here. And then we can send unsuccessfully, or we can send successfully and communicate, but since our send has been consumed, we can never properly receive it. Third, failure, communication. We might have an omission failure, so that just means our message here, instead of going to Q, gets lost. And goes away. Okay, so at this point, what P and Q might want to do is they want to know which of all of these possible end states we're in, because their future behavior will depend on this. For example, they will try again to send, or try again to receive, or or they'll continue, hopefully, if they have everything has worked out. So how do we do that? We have some conditionals. So our conditionals are, first of all, we have a conditional on the sender. If we've successfully sent, then we do this, otherwise we do that. If we've successfully received, then we do this, otherwise we do that. If we've successfully received a specific label, so that's how we communicate a choice at P to Q, we send a label, then we do this, otherwise we do that. Of course, we can't check locally whether messages have been lost, so that makes things more complicated, but we can at least check for some failures. And using these conditionals, we can program some recovery strategies. So one benefit from having separate send and receive primitives is that we don't have to try the same number of times to send as we do try to receive, which is useful because if the send fails 5 times, well, the receive might still succeed the first time. So no point in receiving too many times. So, but we still want to be able to program something that kind of looks like this little arrow here, syntactic sugar. So one way we do that, we have, for example, a send with exponential backoff. So that looks like this. We define this as a recursive function, send with exponential backoff. It is parametric on the process and the frame we're using. And it is tagged with the expression because making it parametric on the expressions is a pain in the ass, and also it doesn't really relate to what we're doing, so we haven't done that. So what we have is, if we have not yet succeeded in sending, then we wait from 2 to the power of n time and return a new n, which is n, the previous n plus 1. And then we try to send, and then we call recursively. Once we've succeeded in our little in sending, then we finish. Another thing for receive, we might want to receive with a timeout. We try to receive the timeout. Again, Q tries to receive on K prime. So if we've not yet timed out, which is to say timeout is more than 0, and we've not yet succeeded, then we update our time, try to receive, and use the stored time to remove some time from the timeout and call recursively. And we can use these to get this little arrow here. So what this says is that P is going to try to send to T and going to try to send to Q something of type T that has, and Q is going to have a timeout of T. So we declare the communication. We set n to 0. So that's our time that we have to wait to send. That starts out at 0. We send our timeout time to T, and then we call our 2 functions. And you can write, we get something resembling the standard communication primitive for choreographies. So now, what do we want to hold for our choreographies? Normally with choreographies, what we want is A, an operational correspondence between our choreographies semantics and our local semantics, and B, deadlock freedom. Now deadlock freedom, very easy. You can just fail, never deadlock. Everything's very simple, so that's not very interesting to try to prove. Operational correspondence between choreographies and local semantics, also not that interesting, honestly. We have, the main thing we have is this gets projected to one action each at K at P and Q, and they count the timers up, they create the frames, they initialize same as they do in the choreography. Pretty simple, so not that interesting. What do we want instead? Well, what we would like to have is that our communication is at most once and best effort. So we don't want to be trying to receive when there is no chance that the message has been sent yet, and we also don't want to be trying to receive something that we have already received, basically. And also, we don't want any unnecessary conditionals, because we don't, well, you don't want to be writing extra code, do you? So how do we get that? We need some static analysis. We have what we call our robustness system. And robustness looks like this. I'm sorry, it does. You can't get out of this. It is technical. There's a lot of things in there. But yeah, this is what we need. So what we have here is something that sort of looks like a Hoare logic, in that we have F0 being the state or before we execute C, and F1 being the state after we execute C. So what is in these states? Well, so these kinds of pairs of a frame, k at p, and the current possible states of the frame. So when we first initialize it, it puts on a hat. And it doesn't take the hat off until it is certain that it is done with whatever communication it has to execute. Additionally, what we have here is a label L, which means that it is possible at this point that P has sent L on K, but we don't know because the hat's still there, so we're not certain. It could be that nothing's happened. On the other hand, if you don't have a hat and you instead have just one state, which is a bullet, that means we are certain that a value has been received. So how do we use that to get our, need P and R first. P is a list of connected pairs of frames, so a sender and a receiver. You need to know which frames are connected to which, and R is the judgment of our predefined processes. So, for example, send with exponential backoff, you start out not having sent anything on the frame, and by the end, you have sent something. So how do we ensure there are no unnecessary checks? Well, when we're checking whether a receive has succeeded, we need the state before that to be that it has the hat, so it can potentially not have done anything, but it also has something that isn't the hat, so it can potentially have done something. And then we split these two states for the two continuations, because which continuation we use depends on which state we're in. How do we check that we only receive at most once? Well, also pretty simple. So when we're receiving something on C, what we do is we check that it must have a state which is only the hat, which means we are guaranteed that it's not done anything. And then we add whatever its corresponding sender has in its state to the state. And then we need to use the conditional on the previous slides to remove this and go into C2 before we can send again, because we need, otherwise, because the requirement of the state down here. How do we check? Well, there are some systems where you don't have omission failure. In this case, you might want to send at most once. So for that to happen, we use our send rules, and we again ensure that the state is the hat, and then we add a new whatever S is to the state. Very similarly, best effort communication is also ensured by our receive rule, because it checks that that there must be something in the in queue in the corresponding receiver. It must have at least tried to send something. It must be possible in this that it is in a state where it has sent something. That's what best communication is. So, conclusion. What is the benefit of using choreographies in this setting? Well, we keep our frame counters synchronized. We can write our custom communication arrows and syntactic sugar, and we can do our static analysis, which we could not do if we had two separate programs, or multiple separate programs. Sorry, just finishing. Give me 1 second. And what guarantees do we get? Well, we get the guarantee that we do not have any dead branches. We have at most once communication, and we have best static communication. All right.
Thank you for your presentation. We have time for one question, if you have it. Thank you, Andrew.
Can I? Okay. So thanks, Eva, for the nice presentation. Just one quick question about the language.
Mm-hmm.
You have these send and receives that are kind of decoupled now, which goes a bit against the idea of choreography.
Right.
Maybe because I'm still a bit confused, of course, but where is the choreography there? I mean, these send and receives, can they be scattered anywhere in the choreography, or they have to be close to this case? Was it frames? Do you call
frames.
them?
No, I mean, you can create a frame and then use it much later in the choreography if you want. So the main thing is our this receive rule. What we ensure is that before we try to receive, there must be one send already have happened on the same frame. So that's the main coupling between them. And then obviously that we have this declaration which happens separately as the two, but it happens sort of the same number of times. So you can always make sure that they agree on which communication is which, basically.
Okay, thanks again for your presentation, Eva. Next, we